j equal 1 to infinity, complete orthonormal system, then the Bergman kernel is given by just the sum to infinity. So yesterday I put two variables, the w, and define this to be f z w. But for today and later, I only use this restriction to the diagonal. So let me just simplify the notation and put z1. Then this is the Bergman kernel. It happened that yesterday Professor said that I'll give another definition of the Bergman kernel. So following his method, I can say that this is given by sup of fz such that f in A2 and L2 norm equals 1. Okay. So in his talk, it's a compact case. So if you do this type of definition, this is just a finite dimension, and you have just complete orthonormal basis, and everything is smooth. And for each choice of bundle, it's easy. But here, we always have infinite number of functions, so the summing up is almost impossible. Okay, this was the situation. Then I started to say that I want to construct invariants out of Bergman kernel. So I first have to prove the invariance, biholomorphic invariance of the Bergman kernel. Okay. So here, the problem here is, in order to define L2 metric, I use some volume elements. So this is a standard Lebesgue measure for Cn. So this is not coming from complex structure. So I have to say why it is invariant. So the setting is that if you have two domains, then you have two Bergman kernels. B2, these are Bergman kernel. So what's the relation between these two? So to do this, I will follow this definition. So suppose you have a complete orthonormal basis. This is two complete orthonormal system for A2 omega 2, then prove back these. So I want to prove back by F, but this is holomorphic, but not orthonormal. Yes, so I have to scale it. So here is a volume form for each. If you prove back this volume form by F, also prove back upstairs. That's given by determinant of F prime square dB. So in my notation, this is so Fz equal W, and F prime means Z, okay, Wj Zk, Jk runs through 1, and so this is n times n matrix. It take determinant. This is a complex determinant. So the provback is scaled by the square norm of this determinant. So this is an easy calculation. So the good thing is determinant of a holomorphic Jacobian is holomorphic. So I can put determinant F prime here. Okay, so this is, I have to define this to be fj1. Okay, not just a pullback of 2, pullback and scale it by the determinant of Jacobi. Then, this is a complete orthonormal system for A2 omega 1. So just sum up these. So starting with Z, this is F1 JZ squared. So substitute this formula. Then every term has same factor, so just factor out first. You have determinant. Square F2. Okay, this is cool. Square. So this is just, I'm copying this, times, this is B2 composed with F. Okay, so this simple calculation shows the transformation rule. So let me write this as a proposition. So B1Z equals determinant prime Z squared B2 FZ. So pulling back doesn't preserve the kernel function, but by scaling the holomorphic Jacobian, that's transformed nicely. In other words, B1 Z dB. So consider function as a volume form. Then this is equals to, it's better not to write, okay, 2W, volume for W. So this is a volume for Z. So this is the same thing. So if you use volume form, the transformation will be written in this form. So this volume form is preserved by a pullback. Or if you write the scaling of the volume form, it is in this form. So sometimes this is easy, useful for calculation. Sometimes this is easy to understand the concept. So I have to use both. Okay. So by using this transformation rule, I can calculate other example of Bergman kernel. So this is also important. It's a Siegel domain. So this is given by D, Z, C, and so let me use W for now. Because, W for now. It's given by imaginary part of W1 is W prime square, and W prime is W2 to Wn. Okay. When n equals 1, we don't have this term, so this is just 0. So this is not important. When n equals 1, dd equals just imaginary part of W positive. Okay. So it's a right half plane, and the disk. Oh, sorry, sorry. Yeah, usually the real parts. Okay, so I changed notation. Thank you. So disk is another good model, and in one complex variable, upper half is also good model, and there's a bihomorphic transformation that's called Kelly transform. So this is a higher dimensional analog of this upper half plane. Then we want to make this bihomorphic to the ball. It should be strict, it should be convex. So you need to put this to make it complex. So it's not really complex, but not strongly convex because it contains a line in this direction. That this should be the real part of W1. And maybe this is the direction of W prime, and this is the direction of imaginary. So this up is this domain. So it's curved with a line contained here. Okay, this is called Siegel domain. This is bihomorphic to the ball. So this is the ball. So we know the Bergman kernel for here, so we can calculate the Bergman kernel for the Siegel domain by using this transformation rule. So let me do this. So Z into W. So the formula is explicitly given. For the first variable, this is just a Kelly transform in one dimension. This one sends ball to the disk to the upper half plane. And for other, you should use this Zj. And the, okay, so maybe it may be helpful to write the inverse. Maybe I use this. Okay, so this is the Kelly transform, sending ball to the Siegel domain. So what is the determinant? So this is given by not 1. Okay, it's not difficult. Then compute defining function W1 minus, no, this should be W. So compute this in terms of Z. Substitute this, then it should be square. It's a just straightforward calculation. So this positive means Siegel domain, and this positive means ball. Okay, that's clear. So this should be correct. And here's some extra term that should be coming from the determinant. Okay, so we know that Bergman kernel for the ball, this is some constant. Okay, we know this. And this is exactly this. So putting this term here, you get Cn minus 2 plus 1. So this one comes here, and then imaginary part of W1 W prime square minus n minus 1. And this is exactly this term. This compare these two. Oh, two. Something wrong. 2i. Is this correct? Factoring out, I should have, the answer should be BB, W should be Cn, or imaginary part W1 minus N minus 1. This should be the answer. So this should be the one, but we have some factor of 2. This one, or its inverse. Okay. Some mistake. 3-1, that should be true. Going back. I haven't checked if you have this constants here or not. Okay, the fact is that this is correct and this is correct. So this should be correct by this. So maybe this looks strange, or I have to consider its inverse. Determinant have been divided by this. Yeah, this is take square, then you still have 2, so you have 4. 4. Maybe some mistake in somewhere. Okay, let me leave it, and everyone can check this. So this is true, and maybe somewhere factor 2 is missing, or I have forgotten. This may not be true. Okay. So the important thing is that these both two formula looks quite similar. Okay. So in both cases, we have B equals Cn rho minus n minus 1 for Borah and D. And in each case, rho is z squared, rho equals something very simple. So natural guess is that question B equals rho some constant, maybe same constant, defining function rho so for this example, this is true, and for other case, there's no way to compute. So easy guess is this, and wow, people believe this. And I think Hörmander tried to prove this for strictly pseudo-convex domain. But later, Fetterman showed that this is not true. You have more singularity. So I will go back to this point later. But this is true up to some order. So this is a term Hörmander. While we cannot compute Bergman kernel explicitly, we can approximately compute. So the first step is the leading part. What is some constant and what's the good choice of a defined function to the first jet? So omega strictly pseudo-convex, C infinity boundary, as always. Then BZ should be Cn. Cn is always the same. Okay, what was Cn? Cn is inverse of the volume of the unit ball. Maybe. Then this is J rho minus n minus 1 plus O2 rho minus n. So this Cn is n factorial pi n, same as the case of these two examples. And J, so there's no space, and I should not cross this. Let me go back here. This J is very important. Where J rho equals determinant of rho J, rho K bar, rho J K bar, where J K runs through 1 to n, 1 to n. So this is a n plus 1 times n plus 1 matrix, and these indices mean derivative. So if you have a conjugate, that is a conjugate derivative, and you have two, it's a second order, dj. Oh. It looks a little bit strange because we have second order and first order and zeroth order, but later I'll show you. Yes?
Are you assuming that the gradient of rho is 1 along the hypersurface?
A gradient law, no restriction, just non-zero.
Oh, because of rho to the power minus n minus 1.
Ah, okay. So this is a defining function. I only assume that the rho not zero. Yeah, if you scale this, it's nicely scaled with J, so you get the same answer. That's a good question. I'll go back to that point later. Yeah, that's a very important calculation here. Okay, so maybe this is called Levy matrix. It appears in the several complex variable in many cases, and later I show you this is coming from a Kähler-Einstein equation, or coming from the formula for the rich curvature. Okay. So this determines the first order of singularity of the Bergman kernel. So let me check. This is true for the ball. That's also important to know. So example is always ball because we have no other example. So ball and low. Let me put it looks like an index not good. Okay. So rho equals 1 minus z squared. Then if you apply j to this is a minus 1 to the n determinant of minus gj bar minus gk, and here Kronecker delta jk. Okay, so if you do some linear algebra, expand the first row, first term gives 1 minus z squared, And the other term always gives 2 square Gn square. It should be so here's the minuses, so I have to put -1 to the n. And it should be n plus 1 or minus. Always make a mistake. It should be minus. It should be minus. Factoring out, cancel with this. Go back to the same thing. So start with this defining function, put in here. No, it shouldn't be true. Oh, sorry, it should be plus. Okay, this one should, sorry. Okay, 1 to n. So this one coming from here, and for each variable you have squared by expanding each term here. So this coming from this minus and this minus, and this minus and this minus should cancel. Okay. So this and this cancels. So finally you get 1. Okay. This is true. So in this case, J rho equals 1. So not just the boundary value. This is exactly 1 everywhere. So in that Hörmander's formula, putting a rho here means nothing. It is just 0 on the boundary. You can put 0 here, but if you consider J as a differential operator on the domain, whole domain, it turns out this is 1 everywhere on the domain. And this is also true for the Siegel domain. So if you start with that defining function and compute, that's much easier. You also get 1. So whenever you get 1 for this operator, it gives nice formula for the Bergman kernel. So natural guess or natural strategy is consider following equation. So Bergman kernel has such formula. So try to fix rho by normalizing this term to be 1 inside. So consider Monge-Ampere equation. That is J rho equals 1 on omega, and rho is a defining function of omega. So in the beginning, I said everything is smooth, but when you consider this kinds of equation, this may be too strong. So maybe at least C2 is reasonable. So if you have a so the idea is solve this equation and use good defining function to describe the Bergman kernel. That's Fetterman's project, and we'll discuss this later. But before doing that, let me do one more important invariant coming from the Bergman kernel. That's a Bergman metric. So yeah.
What are at least some key ideas?
Okay, so this is quite simple. So if you have a domain, strictly pseudo-complex domain, consider a point, and you want to estimate this behavior, then you can approximate this by image of ball. So if you have a ball, by the image, you can approximate strictly pseudo-complex point from the inside to some jet, and also to some order from the outside. And the Bergman kernel can be localized. That means the behavior, boundary behavior of the Bergman kernel is determined by the shape of the domain near the boundary point. So if you approximate a domain by a ball, image of ball, near the point, you can compare these Bergman kernels. So if the domain is larger, Bergman kernel becomes smaller. So there's an estimate upper and lower. So, and we know the Bergman kernel for the ball, that gives an inequality. That works for the, at least for the first jet. But that's very important theorem for the estimate of a Bergman kernel. Okay, Bergman metric. So the Bergman metric is a Kähler metric, complete Kähler metric coming from the Bergman kernel. So this is a Bergman kernel, take log. Bergman kernel is positive always. So you can take log and apply DD bar. And then this should be good. But I1 G equals. So if you like abstract notation, differential form of notation, this is a Kähler form, and this define Bergman metric. If I write more explicitly, this means JK bar equals log BZ JK bar using the index notation for the derivative. So if you No, log, apply log and yes.
So that the entries of the matrix are the J and K bar derivatives of log.
Log DC.
This is a oh,
No.
Those being derivatives?
Yeah, these are derivatives. Oh, it's confusing, sorry. Okay. I don't use this. Okay. It's a Kähler form. So, oh, this is very confusing, sorry. Maybe it's better to write for now. So G or GJK bar. Also, the Bergman metric is G is 1 to n GJK bar DGJ DZ bar K. Okay, this is the Bergman metric. So this is better than the Bergman kernel itself because if we have two domains which are bi-holomorphic, I have proved that Z So Bergman kernel itself is not pullback, but you have this factor. But if you take log, you have log determinant plus log determinant prime conjugate plus log of B2 F. Okay, so if you apply DD bar is just this derivative. Apply holomorphic derivative once and anti-holomorphic derivative once. Then you have DD bar of log B1 equals, this gives 0, because this is holomorphic. Anti-holomorphic derivative kills this term, and this is anti-holomorphic, so Z derivative kills this. So you have this plus DD bar. So I use B2. So I use differential form notation. Otherwise, I have to write Jacobi matrix for F, but DD bar pullback. So here you have some junk terms, but if you apply DD bar, that just goes away. So this is a Bergman metric for the G1. Okay, Bergman metric for the 1 equals 2. So the pullback of Bergman metric on omega 2 is equal to the Bergman metric of G1. It just comes from this transformation rule. So we can say that proposition omega 1, omega 2 by holomorphic, then omega 1 G1 omega 2 G2, these are Bergman metric. Matrix F is isometry. Okay. So we have a biholomorphic map, Bergman metric pull back to the Bergman metric. That means this is isometry. And also from Hörmander estimate, G is complete. So this is if this is strictly pseudo-convex, so this J is always positive on the boundary. So we know this is just taking log of rho minus factor. So the log of rho diverge to negative infinity. So applying DD bar gives a complete Kähler metric. So this gives a nice translation of biholomorphic geometry into Kähler geometry, which is complete. So we can use Kähler geometry to construct so strict pseudo-convex domain is not just a complex manifold. It naturally carries complete scalar metric coming from a Bergman kernel. So everything become a scalar geometry, and if you have a metric, you can construct many things. So you have a curvature and Laplacians, so you can talk about the spectrum of Laplacian, and there's so many theories. But again, unfortunately, we cannot compute Bergman kernel. So it's quite difficult to use Bergman metric itself to compute something explicitly or do some estimate. Nevertheless, Fetterman use Bergman metric to prove extensionism. So the extension theorem says, so you have two domains. The inside is biholomorphic. The boundary corresponds to the boundary, and it extends smoothly. So what he did is consider geodesics with respect to the Bergman metric and consider its image in here. So how the behavior at the boundary of the geodesic. First, he has to do the estimate for the Bergman metric and describe the family of geodesics and show that everything extends smoothly. But the proof is very, very difficult to understand. And nowadays, there are much easy ones. But still, the idea is quite interesting. And to prove this, to prove the extension, he has to really estimate more details of the geodesic. So Hörmander result is not enough. So what he did is following. This is theorem of Fetterman. Omega strip pseudo convex. Then the Bergman kernel has this form. Phi rho to minus n minus 1, psi log rho. And where rho is a infinity defining. Infinity defining function of omega, and this phi and psi are function that smooths up to the boundary. So Hörmander give the leading term, and he showed what is the boundary value of phi. So the boundary value doesn't vanish, and moreover, Fetterman showed that you have this pole-type singularity, and then you have this weak row-type singularity. So for this geodesic estimate, you don't have to know the exact formula for this, but some regularity result of this form, that is good enough to do this. So if you have a type of singularity, you can say something. But then Fetterman think of what are the formula for this? What are the geometric invariant containing this? That's a natural question. So he proposed problem. Compute phi and psi. How to do this? So Hörmander knows the answer for the leading term. And now there's some theory using complex Monge-Ampere equation to describe this phi and psi. So I'll come back to this on maybe Friday. So just one comment on the expansion. Ramadanov conjecture. So the Bergman kernel has this form. So it's far away, so let me copy the formula. Psi equals 0. This is conjecture. So we know that there's no log term for the ball. And if you perturb a ball, it looks like we always something in this form by the variational formula. So it easily gets that it vanishes only for the ball. Okay, so, but there's a simple counterexample. There's a boundary which is locally equivalent to the ball, but globally the domain is not simply connected. That's an easy counterexample. So maybe we should assume that omega is simply connected. Simply connected and log-term vanish, that should be the ball. Bihomorphic to the ball. That's a conjecture, and this is n equal to, yes. This is proved by Robin Graham. 87, more than 30 years ago. And for higher dimension, this is open. Easy to state and difficult to prove. So if you think this as a local question, there's a counterexample. Local means local Ramadanov conjecture says, so we have a domain, boundary point P, take U, neighborhood of P in boundary. Okay, so suppose psi equals 0 on omega times U. Just consider this piece. It is maybe just small neighborhood. Then to omega 0 B. So there should be some map such that so here's a ball. Say fix one boundary point P0, any point is same. Take V, and send this to this. So everything localized. Just consider point and cut the small neighborhood. And suppose log term vanish only on this neighborhood. We don't care what's happened for the boundary elsewhere, but then it should be true. This is the question. To this with Fp equals P0 in the boundary. So this is just a local version. And actually, this is yes. For n equals 2. So Robin Graham proved this. For this is psi equals O2 rho squared, weaker version. So by this weaker assumption, Robin Graham proved that this implied that it is locally equivalent to the ball. But no for higher dimension. So there's an explicit example for which the log term vanishes, but not equivalent to the ball locally. So in that sense, but this example is, for higher dimension, the example is constructed in a complex manifold, domain in complex manifold, which is not Stein. So it can never be embedded into the Cn. So it doesn't give counter example to this global question. So local versions of the global turns out to be different. So the conjecture seems to be quite difficult. Yeah. Yeah. Yes. For that, so near the ball, this is true. So I have a parameter a and an. If you perturb these parameters, you always have log term. So this is true. This is true for the ellipsoid near the ball. For small neighborhood, it is true. But in general, I don't know. Yeah, that's my thesis. Yeah, in my thesis, I use the ellipsoid to try to solve this, but I can do just near the ball, this is true. Yeah, just computing a second variation. Yeah, that is quite tricky, even for the ellipsoid. So for the ellipsoid, that's explicit. You have parameter a1 to an, and try to compute this, taking a derivative in a1 to an. So first derivative vanish at the ball. So I have to compute the second derivative, and that's non-trivial. So I can say this is non-zero for the ellipsoid, not equivalent to the ball. But for high, but you have to really consider global question. So this is a interest question. I will show a proof of this case later as an application of Fetterman's problem, how to write down log term. Okay, now go back to the So the Bergman metric is easy to define, but difficult to compute. So we want to construct a metric which is not easy to define, but we can compute. That's something come from Monge-Ampere equation. So let me set up the problem. Parametric omega. So rho positive. Suppose rho positive define this. Then you can define metric by taking rho. So when omega is strictly convex, this is all putting minus. This is always positive definite near the boundary. For the inside, there is no control, but near the boundary, this is positive definite. So as this is positive. And this is complete Kähler metric, always. But there's so many choice of rho, you can take anything. So let me just write, so I use notation. Put rho, everything depending on rho. So Kähler metric depending on rho. So G rho equals this equals this. So you have to be careful. So we're gonna make good choice of defining function. Then Ricci curvature. So near the boundary, I think for any choice of defining function, this is positive definite. This taking log and
In all
directions near the boundary. It should be true. Inside, you have to assume something. Yeah, if you expand this, so yeah, just do this. This is true. Yeah. Then Ricci curvature is given by minus of log of determinant of G, Jk, k. And this was explained in Professor Datta's talk. So you know what is Ricci curvature, what's the geometric meaning. So then we impose Einstein equation. G, Jk rho equals minus lambda Ricci G Jk. So lambda is a constant, which is not so important, but let me choose n plus 1. That's a good choice for this. So this equation has nothing to do with the coordinate. Okay. So here I use coordinate to define metric, and it looks like there's a coordinate, but you can write this without using coordinate, just dd bar. So this is intrinsic to the complex structure, and so you have some equation that may determine rho uniquely. So then proposition is that so G rho equals minus n minus Ricci of G rho if and only if J, here comes the Monge-Ampere equation, equals E to F. Okay. So here comes the Monge-Ampere operator. This is another geometric definition, geometric derivation of the Monge-Ampere operator. So the Einstein equation is this. And if you write in terms of potential function, this should be written in this form. So you don't like this F. This is, so should be real value function, which is pure harmonic, because this is an equation on the metric level. And you are taking a second derivative of the potential. So if you scale low by E to F, like that, that gives something plus F, that will kill by dd bar. So this ambiguity stays here. So this is not essential. You can just set F to be 0 and make metric. So there's ambiguity coming from just a kernel of dd bar. So our plan is you starting from Einstein equation, consider the Monge-Ampere equation, 0 equals 1, solve it approximately, and use this to describe Bergman kernel, also to construct invariants of the domain. So that's a plan of this lecture series. So tomorrow, I will solve this equation, n plus 2. So I want to solve equal 1, but this is very difficult. So adding this error term, you can really compute just using linear algebra. And that's good enough to do many differential geometry, and you can really compute many things. Okay, let me stop here.